Okay, all right. So before we begin, okay, any question for chapter 3, design of restraint beam? Any question? Assignment? Have you completed? None of you have submit. Okay. So I give you ample time until 16 November to submit the assignment. So please do and submit. Okay, so we will start a new chapter today. Okay, to prevent. Right, let's start. So we have learned about design of restraint beam. So as I explained before, restraint, you need to prevent the beam from twisting, prevent the beam from twisting. So what you have to do is you restrain the top flange of the beam. So if you are unable to restrain the top flange, then your beam will be considered as unrestrained beam. Okay, so these are the cases for unrestrained beam. Okay, the cases for unrestrained beam when subject to loading. When subject to loading. So you can see from these three pictures, all the beam twisted, twisted. So what happened is that once the beam twisted, so the strength, the resistance of the beam dropped, because of the lateral movement. So the beam may not achieve the full moment capacity. Okay, so before this, we design restraint beam. We check the bending resistance. Okay, we check the bending resistance. We have MCRD. That is the full strength, of the beam. But when beam twisted like this, uh, the beam cannot achieve the full strength, cannot achieve the MCRD. So it will fail before we achieve the MCRD. And this um, this failure mode, we call it lateral torsional buckling. Lateral torsional buckling. Okay. So any beam without restraint on the top flange any beam without the restraint about the top flange, we call it unrestrained beam. So other than these four figures in the slide, these are the common cases where the beams are considered as unrestrained. Okay, these beams are considered as unrestrained, and then we have to check the lateral torsional buckling resistance of this beam. Okay, so the procedure to design this unrestrained beam is similar to restrained beam, plus to check the lateral torsional buckling, of the beam. So there's one additional check uh, uh, compared to restrained beam. Okay, so what is lateral torsional buckling? So it's a failure mode, okay, failure mode for beam, and then the beam is slender. The beam is slender. Slender means the length over the cross-section area. The length over the cross-section area is large. It's large. It's relatively large. So we call it a slender beam. And then without continuous lateral restraint. So along the beam, there is no restraint. There is no restraint along the beam. So this beam, when subject to loading, lateral torsional buckling will occur. Lateral torsional buckling will occur. So if we provide lateral restraint, then your beam will become restrained beam. Okay? If you provide lateral restraint, then your beam will become restrained beam. And then you check only the implant bending, like what we do in chapter 3. Okay. So there are certain cases when your beam is unrestrained. Okay? When your beam is unrestrained, but you don't have to check for lateral torsion buckling. There are certain cases you don't have to check lateral torsional buckling, even though your beams are unrestrained. Okay, so we call it can be discounted. No need to check for lateral torsional buckling. When your beam is subjected to minor axis bending, like in this picture, bending about minor axis. When you arrange your beam like this is bending about zigzag axis, bending about zigzag axis, bending about minor axis. When your beam is bending about zigzag axis, you don't have to check for lateral torsional buckling. The second case is when you use CHS, SHS, circular or square bar. Okay, CHS is circular hollow section. SHS, square hollow section. Okay, so if both hollow sections are used as beam, you don't have to check for lateral torsional buckling. Okay, circular and square bar means the shape is circular or square, but it is a solid member. Bar means a solid square, solid circular. These two types of beam, you don't have to check for lateral torsional buckling. Okay. One more thing is fully restrained beam. Of course, like chapter 3, we restrain the top flange. Then you don't have to check for lateral torsional buckling. And last is when you found that lambda LT bar less than 0.2 or 0.4 in some cases, then you don't have to check for lateral torsional buckling. Okay. What is lambda LT bar? Lambda LT bar is called the non-dimensional slenderness. Okay, just now we say slender beam, right? Only slender beam will have lateral torsional buckling. Lambda LT bar is the non-dimensional slenderness or beam. So meaning that if this value, when this value less than 0.2 or 0.4, then your beam is not slender. Okay, your beam is not slender in this case. Lambda LT bar less than 0.2 or 0.4 in some cases, then your beam is non-slender. Okay, it's non-slender. So when non-slender, you don't have to check for lateral torsional buckling. Okay. This is another failure due to lateral torsional buckling. Okay, so lateral torsional buckling, lateral torsional buckling is twisting of beam. So it's shifted sideways, and then it failed. So provided if you have a continuous beam, continuous beam with three supports, three supports, then your beam will twist in a wave form, Because of this lateral restraint, your beam is not able to twist. Okay? You prevent the beam from twisting at the support. So your beam will tend to shift, it will twist from support to another support. Okay? From support to another support, it twists. So the blue color line shows the shape, the buckling shape of the beam. So from one end to another end, from one support to another support, and then from the middle support to the other support. So this is the buckling shape, of the beam. Okay, so lateral restraint doesn't have to be support. So when we say support, so we have beam to beam, okay? Beam to beam or beam to column. Okay, so we have beam supported by column. We have beam supported by beam. So these two common cases that we found, that is the support of our beam. Column support beam, or beam support beam. Okay, so meaning that the lateral restraint here, can be column, can be beam. Okay, can be column, can be beam. So when you have support from, support at both ends, it's possible to have another intermediate restraint, another support for, using the beam, Okay, so this lateral restraint is a general terms. It can be column, and it can be beams, segments of the beam. Okay, so these are the case. Okay, these are the case. When your restraint, is from the beam, so this kind of connections, provide lateral restraint. Okay, Okay, the lateral restraint prevent the beam, prevent the primary beam. This black color beam, this is our primary beam. So when you have a secondary beam connected to the primary beam, we call this a lateral restraint. Okay, we call this a lateral restraint. Yes. Then when we provide a fixed end, fixed in the concrete, this is end support. Again, we have lateral restraint at the end of the beam. Okay, in this case, we have secondary beam provides lateral restraint to primary beam at the connected point. So these two black color I beam, is laterally restrained by the secondary beam on both sides. So this is the lateral restraint. Okay, the lateral restraint provided to the primary beam. Okay, at the point. Okay, so to design unrestrained beam, okay, the procedure is exactly the same like restrained beam, except you have to check lateral torsional buckling resistance, LTB. The LTB, lateral torsional buckling resistance. So according to EC3, Eurocode 3, EC3, there are three methods to check or to get the resistance against lateral torsional buckling. Three methods to check. So we have the primary method. Okay, using the buckling curve. Okay, the primary method using the buckling curve, okay, which is given by equation 6.56 and 6.57. Okay, 6.56 and 6.57, which is given in clause 6.3.2.2 and also 6.3.2.3. Let's see. Lateral torsional buckling. Okay, we have clause 6.3.2.2 and 6.3.2.3. Okay, so these are the two clauses under the primary method. Okay, primary method. And then we have second method is called the simplified assessment method. Simplified assessment method set out in clause 6.3.2.4. Okay, 6.3.2.4. Okay, this is the simplified assessment method. Okay, the second method, second method. And then we have third is general method. General method is 6.3.4. Okay, general method for lateral and lateral torsional buckling, even in clause 6.3.4. Okay. General method for lateral and lateral torsional buckling for structural component. Okay, so we have three methods, three methods to design or to check the lateral torsional buckling according to EC3. Okay, according to EC3. So what we are going to use is the primary method. Okay, the primary method. The other two we don't recommend. We don't teach you on how to use these two methods. We will use only the primary method. So primary method, we have general case and the row section or equivalent method section. And to simplify, to make it simple, so we adopt only 6.3.2.2, the general case. Okay. We only use primary method, general case. Okay. Remember, we use primary method, general case. Okay. So according to Eurocode 3, EC3, okay, to get the buckling resistance. Okay, so we have to get the lateral torsional buckling resistance. The symbol is MBRD. Okay, MB. MB means buckling moment resistance. Okay. So for unrestrained beam, buckling moment resistance is given by chi LT. Chi, this is not X, chi LT WFY divided by gamma M1. Okay, so W is the section modulus. Depend on your section classification. Fy is the yield strength. Gamma M1 is the partial safety factor. So the only thing here, the chi is the one that determine the resistance. The most important parameter, the most important parameter to determine your buckling moment resistance. Okay? Because WFY, WY, FY, gamma M1 is all from the restraint beam. It seems like restraint beam. The only difference is you have to multiply with the reduction factor for lateral torsional buckling, chi LP, reduction factor. Okay, so under the general case, clause 6.3.2.2, in order to get the reduction factor, chi LP, okay, in order to get the reduction factor, we have a formula. We have a formula 1 over phi, phi LT plus square root of phi LT square minus lambda LT square bar. Lambda LT bar square. So this is the formula to get the reduction factor. And reduction factor, okay, the name is reduction, therefore it cannot be more than 1. Okay, because we need to get a lesser value, the reduction. So it cannot be more than 1. The maximum, okay, the limit is 1 at 1.0. Okay, and then to get the phi LT, is given by 0.5 multiplied with 1 plus alpha LT. Okay, alpha LT is the imperfection factor from table 6.3. Okay, and then we multiply with lambda LT bar minus 0.2. Okay, remember just now we have a clause, we have a condition saying that if your lambda LT bar less than 0.2, you don't have to check for lateral torsional buckling. Okay, so here is where the 0.2 come in. Okay, if you get your lambda LT bar 0.2 or less than 0.2, your reduction factor will be 1.0. Okay, if your lambda LT bar equals to 0.2 or less than 0.2, you can stop calculate the reduction factor because your reduction factor will become 1.0. Okay, so meaning that lateral torsional buckling will not occur. Okay, lateral torsional buckling will not occur if you get your lambda LT bar less than 0.2. Okay, so after you calculate the phi LT, after you calculate your phi LT, then you will replace in the formula here. Okay, replace in the formula for chi LT. And then to get the buckling curve, when do we use buckling curve? Buckling curve is somewhere here, right? With the alpha LT. Alpha LT, the imperfection factor, actually comes from the buckling curve. Okay, so buckling curve is given by curve A, curve B, curve C, curve D. Okay, we have 4 curves here. Okay, we have 4 curves here. So to choose the buckling curve for our beam, okay, to get the imperfection factor, to get the imperfection factor alpha, we refer to buckling curve, and to choose the buckling curve, we refer to our section. Okay, so if you are using hot roll I section, okay, if you're using hot roll I section, if your H over B is less than or equals to 2, you choose curve A. If your H over B more than 2, you choose curve B. So H is the depth, B is the width, from the section property table. Okay. H is the depth of the beam, B is the width of the flank. So you divide H by B, you get the value. You get the ratio. Okay? If your ratio is less than 2, and then you choose curve A. If your ratio more than 2, you choose curve B. Okay, it's built up section. Okay, built up section, meaning that not from the section property table. Built up section, welded section, not from the section property table. Then you will use curve C or curve D. Okay, you will use curve C or curve D. Okay, if you are using other cross section, for example, channel, okay, C channel or rectangular hollow section, or angle section, which is not I shaped. Then you use curve D. Okay, you use curve D. Okay, so each buckling curve comes with a imperfection factor. Okay, each buckling curve comes with imperfection factor. So the alpha LT that we want to use here is from buckling curve. Okay, we have 4 values, 4 curve, then 4 alpha value from 0.21 up to 0.76. So the more imperfection factor, okay, the higher values for imperfection factor will give you a lower reduction factor. Okay, will give you a lower reduction factor, meaning that more reduction. Okay, if small value for chi, meaning that you have more reduction. Then your buckling resistance will be lesser. So we call curve A is the highest curve, and curve D is the lowest curve that gives you a lower resistance. So if you look at your code, Euro code 3, this is the shapes of the buckling curve. And this is the shape of the buckling curve. We have curve A, B, C, and D. So A is the highest. Yeah, of course, we have A naught, but we don't use this A naught for lambda. We don't use this for lateral torsional buckling. Okay, A naught is not for lateral torsional buckling. We use A until D for lateral torsional buckling. So curve A is the highest curve, curve D is the lowest curve. So you see curve A with the same non-dimensional slenderness has a higher reduction factor. Curve D give you a lower reduction factor, means lower resistance. So this is another method. It's under the primary method, but for roll or equivalent welded section case. Okay, so we don't suggest you to use this because it's more consideration in the calculation. So the difference with the general case, the difference with the general case is we have this beta factor. Okay, in the formula, we have this beta factor, and then the limit is either 1 or we have 1 over lambda LT bar squared. We have two limits that we have to check. And then for the calculation of phi, okay, we don't use 0.2. Okay, we don't use 0.2. We use lambda LT naught bar. We use lambda LT naught bar. So this lambda LT naught bar suggested by the code is 0.4. Okay, not 0.2. And this is suggested by code 0.4. Okay, and then we have beta again in the formula. So you are using this method, this roll or equivalent welded section case. You have to consider beta. You have to consider lambda LT naught bar. Okay, so that's the difference. Okay, the difference between the two methods. Of course, the general case, a simpler case, will give you a more conservative value. Okay, give you a more conservative value. So the red line represents the general method. The blue line represents the roll or equivalent welded section case. So blue lines give you a higher reduction factor, meaning that less reduction in the resistance. So in the end, you will get a higher buckling moment resistance if you are using the roll method. If you're using the general method, you have a lower value for your buckling resistance. You have a lower value, but both are acceptable. Right? Both are accepted in this EC3. Both can be used. Okay? Both are safe to be used to check the buckling moment resistance. Okay. So just now we have non-dimensional slenderness lambda LT bar. So to calculate the non-dimensional slenderness, the formula is given by lambda LT bar equals to square root of WYFY divided by MCR. Okay, so W depends on the section classification. So it can be plastic modulus, it can be elastic modulus. Depend on your section classification. Fy is the yield strength of the material. Depend on the steel grade. Refer to table 3.1. And then we have MCR. MCR here is the elastic critical lateral torsional buckling moment. Elastic critical lateral torsional buckling moment. Okay, to calculate MCR, okay, for typical end condition and under uniform moment, okay, the elastic critical lateral torsional buckling moment MCR is pi square EIZ over LCR square times square root, okay, so 0.5 is square root of IW divided by IZ plus LCR square times GIP divided by pi square EIZ. Okay. This is the formula for MCR, provided the moment is uniform. Okay, uniform moment means the value of M, the MED, along the beam, is the same. Is the same. So what is this? Let me see. Okay, so this is your beam. And then your beam has a moment. So your moment, bending moment for your beam is the same, uniform. We call this uniform moment from one end to the other end, and along the beam has a same value of moment. We call this uniform moment. Okay, uniform moment. So uniform moment. Okay, we use this formula. Okay, uniform moment. We use this formula. So in this formula, we have E, the elastic modulus of elasticity, E. And then we have Isaac. Isaac is the minor axis, second moment of area. We have LCR, the buckling length. We have IW, the warping constant. And then we have IT, torsional constant. We have G. G is shear modulus. Okay. So E and G is a fixed value, fixed value. And Isaac, IW, IT is from section property table. Okay, come from section property table. LCR depends on your unrestrained length, the unrestrained length of your beam. Then, yeah, using this, you can calculate your elastic critical moment. Okay. Under non-uniform moment, non-uniform moment means the moment from one end to another end is different. It's different. So it's not a straight line, it's the value along the beam will be different. That's non-uniform moment. So for non-uniform moment, the difference is we have to include the C1 factor. Okay, the rest is the same except we have to multiply with a C1 factor. So this C1 factor, C1 factor can be calculated using formula 1.88 minus 1.4. Then we have this ratio, the ratio for n moment, okay, ratio for n moment. Then we have limit for C1. C1 cannot be more than 2.7. Okay, C1 cannot be more than 2.7. Okay, so by using this equation, you calculate C1, and then C1 cannot be more than 2.7. So the symbol here, okay, not mistaken, is called the omega. Yeah, no, this is called psi. Okay, PSI, psi. This symbol is called psi. Psi is the ratio of n moment, ratio of n moment. So to calculate the psi, we take the n moment divided by another n. Okay, so from this, take this value, the n value here, divide by the n value here. Then you will get a ratio, n moment ratio, psi, from 1 to -1. Okay, from 1 to -1. So each psi has a C1 factor. Okay, it's a C1 factor. And this C1 factor actually comes from this equation. It comes from this equation, you get the C1 factor. Right. So you get the C1 factor, you multiply with the formula here, you get your elastic critical moment. Okay. And if your bending moment is not uniform, it's not n moment, meaning that you have a shape, right? You have a bending moment shape like this. This happens when your beam is without intermediate restraint. Without intermediate restraint, then you will find your beam in this case, either one of this case. So the first is simply supported beam with uniform moment. Yes, simply supported beam with uniform moment. So your C1 factor is 1.132. If your beam is rigidly connected, rigidly connected beam with uniform moment, then your C1 factor is 1.285. Your bending moment diagram will look like this. Then your C1 factor 1.285. And if your beam is simply supported with one concentrated load, okay, so your bending moment diagram looks like a triangle. Then your C1 factor 1.365. Okay, similar case but rigidly connected with rigid connection, then your C1 factor 1.565. And if you have two concentrated load, okay, two concentrated load, and the shape of the bending moment diagram trapezoid, so your C1 factor 1.046. Okay, so this is C1 factor. C1 factor, if your moment is not end moment. This is end moment diagram. End moment diagram. And this is using the equation. And this is the formula for MCR. Okay, LCR. LCR is called the effective length or critical length. Critical length. So critical length very much depends on the end restraint. Okay, so we have rigid or pin connection. So if your beam is rigidly connected, like case 1, okay, so this you can refer to your books. Your books has all these figures like this. So if your beam is connected rigidly to the column, okay, so we call this a rigid connection. Rigid connection. So your LCR, your LCR, the LCR is given by KL. K is the effective length factor, and depend on your connection. So L is the original length of your beam. Okay, so you have to multiply your beam length with effective length factor or effective length parameter. So from 0.7 up to 1. So basically 0.7 referring to rigid connection. And then 0.8 is semi-rigid. And then 1.0 is spin. So your connection, if your connection is spin, you use 1. Your connection is rigid, you use 0.7. If your connection is semi-rigid, you use 0.8. And then case 4 and case 5 is considered as semi-rigid. Semi-rigid. So for rigid connection, we have these examples. For semi-rigid, we have these examples. Okay, for pin, pin, we have this example. If your connection is like this, then your connection is considered as a pin connection. Okay, so basically, that is how we determine the parameters, parameters in the calculation. So the procedure for lateral torsional buckling. So first, we identify the bending moment diagram, BMD, and also SFD, shear force diagram from the design load. And then we choose a section, we get the section properties. 3, we classify the cross section, and we do section classification. 4, we determine the effective buckling length, LCR, depend on the end support connection, the support connection. And 5, we calculate MCR and WYFY. Okay, so at step number 5, we have to get the C1 factor, and then we have to calculate the MCR. So after we get the MCR, we calculate the non-dimensional slenderness, lambda LT bar. And then after we get the non-dimensional slenderness, we want to calculate phi. Okay, phi LT. To get phi LT, we need the imperfection factor. We need an imperfection factor. So we choose the buckling curve. And then we calculate the buckling reduction factor, chi LT. Okay. After that, we insert this reduction factor into our formula MBRD. And then we compare MBRD with the bending moment, with the applied bending moment. If the applied bending moment less than the buckling resistance, so meaning that the beam is safe to be used. And this is procedure to get the buckling moment resistance and to check with the load, the load that we apply. Okay, example, a simply supported primary beam is required to span 10.8 meter and to support two secondary beams as shown below. Secondary beams are connected through fin plates to the web of the primary beam and full lateral restraint may be assumed at this point. Select a suitable member for the primary beam assuming grade S275 steel. Okay, so we have a beam here, ABCD. So we want to design this beam, ABCD. And this beam is 10.8 meter length with two intermediate restraint at point B and C. With two intermediate restraint at point B and C. So our buckling leg for beam ABCD can be divided into three segments, AB, BC, and CD. Okay, because of these two secondary beam, we have two intermediate restraint. So your segment length will be AB, BC, and CD. Okay. And at the same time, the load actually comes from the secondary beam. Okay, the load comes from the secondary beam. So we calculate the reaction. We get 425.1 kilonewton and 319.6 kilonewton for our primary beam. Okay, we have 2-point load here. So segment AB is 2.5 meters, segment BC is 3.2, segment CD is 5.1. This is given in the question. Okay, this is given in the question, given in the example. So after we calculate, we analyze, we get our shear force diagram and bending moment diagram. Okay, we get our shear force diagram, bending moment diagram. So for each segment, we have our shear force and bending moment. Okay, each segment, we have our shear force and bending moment. So for the purpose of this example, lateral torsional buckling curve for the general case will be utilized. Lateral torsional buckling checks to be carried out on segment BC and CD. By inspection, segment AB is not critical. So try 762 by 267 by 173 UKB in grade S275 steel. Okay. So what is this statement means? We use the general case and then we check on this segment BC and CD. Okay. We design only segment BC and segment CD. Why? Because AB, the bending moment diagram for segment AB is similar to CD. The shape. Okay, both are triangles. And then AB has a 2.5 meter length. CD has a 5.1 meter. So if CD, because the beam size is the same, ABCD is one beam and using the same size. When we check for segment CD, okay, the length 5.1 meter with a bending moment of 1362. Okay, if we check segment CD, the beam is adequate, then we can skip the checking for AB because AB is less critical as compared to CD. Okay, AB is less critical as compared to CD. So we check only CD plus BC because BC has non-uniform moment, okay, non-uniform moment, and has a different value, different moment at both ends. So we check only BC and CD. Okay, so for this example, we don't check for shear resistance, we don't check for deflection. We only focus on the lateral torsional buckling. So first, we check the classification. Okay, this is required to get the class of the section. So we conclude our section is class 1. Okay, we conclude our section is class 1. And then we check the moment resistance. And for class 1 section, we use WPLY. And then we get our bending resistance. Bending resistance is 1704. Our maximum bending moment 1362. So cross-section resistance in bending is okay. And then we check segment BC. Okay, we start with segment BC. So segment BC maximum moment is 1362. And then we have a LCR 3200 millimeter. Okay, 3.2 meter, 3.2 meter. And then we calculate MCR. So MCR, we have to get the C1 factor. C1 factor given by this equation. And then we have to calculate psi, the ratio of end moment. So 1194 is from one end, 1362 another end. So we have 0.88. So 0.88 insert into this equation, we get our C1 factor 1.05. So 1.05, you multiply with all these values. Okay, all these values come from section property table. Okay, come from section property table. So we have our MCR 5699 kilonewton meter. And then we calculate the non-dimensional slenderness using the MCR value. We get 0.55. Okay, and then we have to select buckling curve by using H over B ratio 2.85. So the value, the ratio is more than 2. We use buckling curve B. Okay, from table 6.4. Okay, we have to use curve B. So curve B alpha LT, the imperfection factor 0.34. So we insert 0.34 into the equation, and then 0.55 is from our calculation. So we get phi is 0.7. And then last we get our reduction factor equals to 0.87. 0.87. So 0.87 we multiply with our plastic section modulus. They multiply with the yield strength. Okay, our buckling moment resistance is 1479. 1479. Compare to MED, we get a ratio of 0.92, which is less than 1. So we can conclude segment BC is adequate. Segment BC is adequate. Okay, and then we continue with segment CD. Okay, segment CD. The segment CD, the maximum moment 1362. And then our section, we use the same size. So the section is class 1. Okay, then for segment CD, the length is 5.1 meter. So again, we have to calculate the psi value, the end moment ratio. One end is 0, the other end is 1362. So the ratio is 0, and we get our C1 factor 1.88. 1.88. So the rest is the same except the LCR. We change to 5.1 meter. And then C1 factor, we change. So we get MCR 4311. 4311. Then we calculate non-dimensional slenderness, we get 0.63. The buckling curve is the same because depend on the beam size. So the beam size, just now, beam size, just now the beam size give us a ratio of 2.85. So it will be the same for segment CD. So segment CD, segment BC, we have an imperfection factor 0.34. So segment CD also 0.34. So we get our phi equals to 0.76, and last we get our reduction factor 0.83. We multiply 0.83 with WY, FY, and then divide by gamma M1, we get 1411. Okay, so compared to MED 1362, we get a ratio of 0.97. So segment CD is okay, adequate. So BC adequate, CD adequate, AB we skip because it's not critical. Therefore, by checking segment BC and CD, and both checkings are okay, then the beam is safe. This beam size this beam size 762 by 267 by 173, grade 275 is adequate to resist this load. It's adequate to resist this load. Okay, any question? Any question, class? Are you still here with me? Okay, clear? Right.
Yeah,
So, if no question, any more question? Any question?
not this one.
So, chapter 4, basically, we just teach you on how to get the MBRD. Okay, chapter 4, we just teach you how to get the MBRD. Okay, the rest, to check the shear resistance, to check shear buckling, to check deflection, is the same in chapter 3. It's like chapter 3. So to complete a design of unrestrained beam, you have to start with the analysis. Okay, the analysis, section classification, you have to check shear resistance, and then you check the moment resistance, plus checking of MBRD. Okay, check of MBRD, and then if you have wet bearing, wet buckling, you have to check wet bearing, wet buckling. If you have to check the deflection, you check the deflection. So the whole process, the whole process, you have to check everything. Okay, doesn't matter unrestrained or restrained. Restrained, unrestrained, the procedure, the checking is the same. The only difference, unrestrained, you have to get MBRD. Okay? You have to compare with MBRD. So that's the difference. The difference. Right? If no question, then you can try solving the problem. The problems in chapter 4. So again, this is part of your assignment. I have given the questions. I know, not yet. So we have problems and we have answer also. I provide the answer for chapter 4. Okay, if you want to check your answer, you refer to the answer that I provide. And I will also set an assignment for unrestrained beam. So for unrestrained beam, We have problem 4.1 until 4.5. So I want you to do 4.1. Okay, 4.1 is straightforward and simple. 4.4. Okay, 4.1, 4.4, and 4.5. 3 questions. Okay, 4.1, 4.4, 4.5. So you have to do these 3 questions. Do these 3 questions. Okay, maybe you can start with 4.1 first. Okay, using the method that I teach you, you design this unrestrained beam. Design this unrestrained beam. Okay, so you will do 3 questions, 4.1, 4.4, and 4.5, and as assignment. As assignment. So I think here. Assignment for unrestrained. So problem 4.1, 4.4, 4.5. So you did November. Okay, so you have another assignment here. Oh, by the way, I think we have to change, make it earlier. We have to complete before 16. Okay, why 16? Because we have our test on 17. Okay, if you notice, if you realize, I have set the test one date, 17 November. 17 November, Monday, Monday, from 8 to 10. Then the location, the scope, everything is given. And also I have test 2, also we have set the date 7 January. So mark your calendar, these 2 dates. And because I have informed early, so no changes after this. Okay, so our test, we will conduct our test together with other section. So it will be a big crowd doing the test. So bring your own code, Eurocode, EC3, then complete all the assignment before you come. Okay, so yeah, I think that's it for today. Any question?
Okay. Attendance.
Attendance error. Let's see if I still can generate. Something wrong. Okay, scan. Okay, so others, I think that's it. Thank you very much. See you on Monday. Monday. Monday will be physical class again. See you in the class. Okay, thank you very much. See you on Monday.
Doctor, I want to ask